All right. So I think from here we can continue with where we add. Participants. Okay. All right. So I think we should have, we ended on where the question is asking us to come up with thermochemical equations. So thermochemical equations are equations that should always have enthalpy, this at the far end. Now you have to look at the way the question is phrased. They want us to write a thermochemical equation for the standard enthalpy of combustion. So standard enthalpy of combustion is when you burn 1 mole of a given substance. Okay, so 1 mole of a given substance should give you what you are actually looking at. So let us look at question 1. They're saying standard enthalpy of combustion of ethanol. So if you check here, this is ethanol. Okay, ethanol plus oxygen. If the combustion is complete, it should just give you carbon dioxide and water. Now, this is a combustion equation, meaning it produces energy. That is why on the symbol of the enthalpy, I have included the negative sign. Now, every time you write an equation, it should have state symbols and it should be balanced. So if you check here, ethanol, there's a subscript L there representing it is in liquid form. We all know ethanol is an alcohol, therefore is in liquid state. And then from here, you have gaseous oxygen that is used for combustion, gaseous carbon dioxide being produced, and liquid oxygen being produced. So the equation, irrespective of that, the atoms should balance. So you check, I have 2 carbon atoms on my left, 2 carbon atoms on my right, 6 carbon hydrogen atoms on my left, 6 hydrogen atoms on my right. I have 7 oxygens on my, so I'm balancing oxygen. If you check on your right, you have 2 times 2, which is 4, plus this 3, 7. And here there was only 2. So to balance, there are only 3. So to balance, you put 3 there. 3 times 2 is 6, plus 1 is 7, meaning the atoms on my left are reflecting the atoms on my right. And therefore, the equation that I'm using is what? A balanced chemical equation. It turns and becomes a thermochemical equation, or it adopts the name thermochemical equation immediately I bring in the enthalpy symbol. And now, since they have said it's standard, there is a degree on top on my formula there, and also C below, representing standard enthalpy of what? Combustion. Should you just write without this, it's just going to be a standard enthalpy. And if you do not include a C beneath, it means it will just be standard enthalpy, and we will not know what enthalpy you're talking about. So whatever enthalpy you're talking about, you have to specify. The same for the neutralization. You are neutralizing. So what you are neutralizing should always be 1 molar. So you were neutralizing sodium hydroxide. So this is the chemical formula for sodium hydroxide. And there is in brackets here AQ, meaning aqueous, plus HCl aqueous to produce sodium chloride aqueous. The sodium chloride that is produced does not form solid, so it is still in aqueous dissolved, plus H2O, a liquid, and then plus this was the standard enthalpy of neutralization, not just any type of enthalpy. Since it is standard enthalpy of neutralization, you're going to put a 0 there, symbolizing standard. And then what standard enthalpy is, it is neutralization. So N down there. So this is the enthalpy of neutralization. When you put N there, you are actually representing neutralization. So check if the atoms are balanced. 1 sodium on my right, 1 sodium on my left, 1 on my right. 1 oxygen atom on my left, 1 oxygen atom on my right. 2 hydrogen atoms on my left, 2 hydrogen atoms on my right. 1 chlorine atom on my left, 1 chlorine atom on my right, meaning this equation is also what? Balanced. It is a balanced chemical equation, and it becomes a balanced thermochemical equation immediately I show standard enthalpy formula, a symbol there. So without this, it is just like any other equation. It's just a chemical equation. When you bring in this, you mean it is a what? Thermochemical equation. If I bring electrode potential like that, E representing, electrode potential. So if I bring in this symbol here, this will mean it is an electrochemical equation. So if I don't put this, instead I put this, I'm actually talking about an electrochemical equation. So these are the differences that put names to chemical equations. We have chemical equations, and then they become special equations because they are studied under special conditions. So the symbols that you put there, so this was not an electrochemical, so there's no need for that. I was just trying to show you guys that when you find an equation and you find there's that symbol, that means that's a that's an electrochemical equation. Again, there's another question asking us to produce standard enthalpy of phenol. Okay, standard enthalpy of production of formation of phenol. Okay, so if you are forming, standard enthalpy is studied as the formation of 1 mole. So what you have to produce is 1 mole. If you check, this is 1 mole of phenol, then you have to come up with your reactants this side. All right, so when coming up with the reactants, all you have to do is just check what you have. You have 1 carbon, a carbon here, so you can introduce carbon here. Hydrogen, you can introduce hydrogen there. Chlorine, you can introduce chlorine. So when you are forming something, you are not restricted to what you use when forming what you are coming up with, so long as you write the atoms that are reacting to produce what you want. The equation will be marked. At this particular point, we do not really mind that you have written something that actually is going to give you what you're looking for. So what I've written here is that if I combine solid carbon plus gaseous hydrogen plus gaseous chlorine, it will give me phenyl chloride. Okay, so probably this is in gaseous form. And then standard enthalpy. So you write there, standard enthalpy. So you put a 0. This is of formation, like that. So with putting standard enthalpy at the far end, that simply means that is a thermochemical equation. So this thermochemical equation is going to appear in that particular manner. Okay, if you want, you can use any other reagent to actually come up with what you're looking for. So if you check my equation, it is balanced. How many carbon atoms do I have on my right? I have 2. How many do I have on the left? 2. How many hydrogens do I have? I have 2. How many do I have here? I have 3. You have 3 hydrogens. I think it was 3. Let me just counter check on the question. What is the question? C2H3Cl. Yeah. So it is 3 here. So for you to introduce 3 this side, you're going to say 3/2, meaning this 2 cancels that 2 and you only remain with 3 there. So 3/2, 1 chlorine, and here 1/2 chlorine. So the chlorine cancels and that cancels, and then this is what you get for your production. So that is one way in which you can write this particular equation. Or the other method would be a 2-carbon molecule that you know that can have 4 carbon atom is ethene. So you write ethene C2H4 plus Cl2 to give you, so this is a gas. This is a gas to give you C2H3Cl plus HCl, like that. So this is a gas, this is a gas, that is a gas, that is a gas, and that is a gas, like that. And you put standard enthalpy of formation. So this is another way in which you can write your equation. Okay, just by thinking of what compounds can come to your mind, that what organic compounds do you know that can come to your mind to synthesize what you're actually looking at. So I just looked at my product. It has 2 carbon atoms and 3 hydrogen atoms, meaning at best this element can have 4 hydrogen atoms, and then one of the hydrogen atom is replaced by a chlorine atom. So I just remove the chlorine, I replace it by a hydrogen atom, it gives me this. And then chlorine will always come from chlorine, a gas chlorine. So that is the chlorine, a diatomic molecule existing there. And then if this 1 chlorine atom replaces 1 hydrogen atom, the hydrogen atom is not just going to vanish, or the remaining chlorine atom from this one is not just going to vanish. It has to meet up with something. So that is the chlorine, the hydrogen atom coming from here and the chlorine atom coming from there gives you HCl, like that. So that is actually what you have. So at the end of the day, this is how your equation is going to come out like. And if you check out that particular equation, everything in that equation is balanced. So coming up with thermochemical equations is actually very simple. All you have to do is you can use atoms, elements to come up, to combine and give you the product of interest, and everything else follows through. All you have to understand is what is it you're looking for, because at the end of the day, we will first consider the enthalpy you've indicated there. Is it the correct enthalpy? So this is the correct enthalpy because this is standard enthalpy of what? Formation. And the question requested that you write the standard enthalpy of formation. Otherwise, we would have used something totally different. So you can finish up. The ammonia there is for your doing. I've done for you 3 so far on that particular question. So I think it will be right if you guys did some ammonia, and just for practice purposes. All right, so question 12. Question 12 is asking us to calculate the standard enthalpy of formation. Now, standard enthalpy of formation, remember from the definition itself, standard enthalpy of formation is when you produce one more. When you produce one more of your product, that is standard enthalpy of formation. So standard enthalpy of formation for each of the following. So all I'm going to do is I'm going to pick up one equation, and then your product should be 1 molar. So if you check question 2, for instance, you pick up question 2. So question 2, question 2 is 2Na solid plus 2H2O liquid to produce 2 sodium hydroxide aqueous plus H2 gas, like that. So now this is okay. So what has happened? It stopped. Okay, so you have this equation given here. Okay, now for you to produce standard enthalpy, okay, if you are dealing with standard enthalpy, what you're actually going to do is you have to ensure that this equation produces one more of what you want. So if you look at this particular equation, one more should be in reference to sodium hydroxide. This is what we're going to have of interest. So you have 2 moles and not 1 more. Okay. So for this equation to give you 2 moles, what you're going to do is throughout, you're going to divide by 1/2. So here, 1/2, here, 1/2, multiply, there you multiply, and here you multiply by 1/2, and here you multiply by 1/2, like that. So this and this cancels, this and this cancels, this and that cancels. You're going to have sodium solid plus H2O liquid to give you sodium hydroxide aqueous plus 1/2 sodium gas, like that. And you include standard enthalpy of formation, like that. Now, this is how that is supposed to be solved. So you have to know what you are producing in a given equation. And remember, every time you're doing that, it has to be 1 more. No more, no less. 1 more at any given time. So if you check the equation that we're just from solving, you add 2 moles of your product, meaning you needed to get it to 1 more of your product. And for you to do that, that is why we divided throughout, because that is what we actually needed to do, what to produce. So The remaining two questions can be solved in the same manner as we have done for A. So you can solve the other two for practice. If you have any challenges, you can hit my inbox in the mornings tomorrow before our class so that we get to see how well we can work. I can rectify a problem you may face on that one. So we go to question 13. Are there any questions before we start 13? Okay, so question 13. Acetylene burns in air according to the following equation. So you have that equation. Given that the standard enthalpy of formation of carbon dioxide is that, the standard enthalpy of formation of gaseous water is that, what is the standard enthalpy of formation of ethene? Okay, now here, this question is straightforward and very interesting. Remember, when you are calculating the enthalpy of a reaction, what we write is change in enthalpy of reaction, okay, is equals to the sum and change in standard enthalpy of product minus the sum and change in standard enthalpy of reactants. Okay, so this is the equation that we use when we are calculating standard enthalpy. Now, if you check, the standard enthalpy of the reaction has been given as negative 1255.8 kilojoules. So you're going to put it there, negative 1255.8 is equals to the sum of the standard enthalpy of formation of your product. So this N here on the formula, this N on your formula represents the number of moles of each that you're using. So there, for carbon dioxide, in that formula, you have 2 for carbon dioxide. So it's going to be 2 multiplied by, what is the standard enthalpy change of formation of carbon dioxide? Negative 393.5 plus the standard enthalpy of formation of what? Gaseous water. How much is produced? Just 1. So this one has minus 241.8, then minus how much of your, so there you have enthalpy of formation of what? Ethane, and then oxygen exists in that nature, so there's no need for you to write the standard enthalpy of formation of oxygen for yourself. Okay, so there's no need for you to write that one. So all you have to now do is from here, you just now proceed with the calculation. So what is this multiplied by that, and then plus this one here? So 2 multiplied by minus 393.5 plus minus 241.8. What are we getting? So we have here minus 1255.8 is equals to, what is the answer you're getting when you deal with this?
It's negative 1028.8.
Negative 1000.
1028.8.
And then minus the standard, the enthalpy of formation of what we're looking for. So then this closest the equal sign comes this side, you have minus 1255.8 minus 1028.8. This becomes plus, is equals to minus the standard enthalpy of formation of that. So what are you getting when you solve this side?
Negative 227.
Negative 227 is equals to minus standard enthalpy. Now, this should not have a negative sign like that. So divided by 1 like that. Therefore, the standard enthalpy of formation of this is equals to 227 kilojoules. So that is how you arrive at your answer. Is that clear? Any clarity, any questions?
It's clear, sir.
All right, so therefore, we move. Next week, you guys should prepare yourself. You'll be writing an online quiz for observation of how much you've learned so far. We've covered a lot of topics and I'm supposed to be gauging whether or not you guys are understanding. So when we are done with this topic, you are expected, you will be given a week of preparation that is starting from today. We've done 2 topics together, 3 topics actually together. That is the all equilibrium part, and we've now done thermochemistry. So I will give you questions to do on Monday next week. So expect that on Monday, please be ready, be on time. It will be a short assessment and you give me answers to the questions. Okay.
Okay, sir.
All right. And then consider the following reaction, that is 14. Below, calculate the standard enthalpy of formation of the chlorofluoride there. So the chlorofluoride there, they want you to find the standard enthalpy, meaning the formation of 1. And they've given you the standard enthalpy of negative 11986 kilojoules as the standard enthalpy of that particular equation there. So this question and the question I'm from solving, there is no difference. All you have to do is, now, the way this question has come is not the way it can be brought in your test, quiz, or assignment. I mean, an assignment, it can come like this, but in a quiz or in a test or exam, it won't come like this. They should give you the standard enthalpy formation of ammonia. They should give you the standard enthalpy of formation of hydrogen fluoride. The only ones that are not going to give you is chlorine and nitrogen because they are in existence like that. So you don't expect the standard enthalpies of those because their standard enthalpy is what? 0. So those other ones now, because this particular question was an assignment or a tutorial sheet, they expect you to look up the standard enthalpies of these other, especially of ammonia gas. So of ammonia gas and hydrogen fluoride gas here. So only ammonia gas and hydrogen fluoride. Nitrogen gas exists like this, chlorine exists like that. It's in its pure state, therefore the enthalpy, standard enthalpy of formation of these two is definitely 0. Ammonia exists in liquid form, so its gaseous state should have a standard enthalpy which you need to find. So from here, you just write the equation I wrote, standard enthalpy of the reaction being equals to the sum of the enthalpy of products minus the sum of the enthalpy of reactants. And then from there, you carry out the calculation. This is going to be found. This question is straightforward. So for your practice, I've done question 13 that is using the same principle as that being used on question 14. So you will do question 14 for practice. So we go to question 15. Explain exactly what this means. Okay, so here they want you to start doing explanations. The bond dissociation enthalpy of bromine is 198 kilojoules per mole. So what does this statement mean? Bond enthalpy of 193 kilojoules per mole. Now you are looking at dissociation. Dissociation is breaking apart. This simply means that the standard enthalpy of dissociation is the energy required to split, to break the bromine molecule. One more, because they've put here per mole. So this simply means it takes 193 kilojoules of energy to break 1 mole of bromine bonds. Okay, to break the bonds between bromine atoms. So it takes 193 kilojoules of energy to break the bonds between the bromine atom in 1 mole of bromine. So you have to have 1 mole. That is where this energy is applicable. Should you work with anything other than 1 mole, they're not going to put per mole here. The energy is going to change. If you're working with less than a mole, this is going to change. If you're working with more than a mole, this is not going to be per mole. So since it is per mole, meaning it is 1 mole of bromine sample that you have. So that 1 mole of bromine sample, to break the bonds between the bromine atoms, it simply means you will need to put in 193 kilojoules of energy. That is what bond dissociation enthalpy means when it is given as per mole. So the same means here, the mean bond enthalpy. Now, look out for this word, mean. Mean means average. So the average bond enthalpy of carbon-hydrogen bond in methane is 411.05 kilojoules per mole. This simply means that the average bond contained in the bond between chlorine and hydrogen, okay? The average energy contained in the bond between chlorine and carbon in 1 mole of methane is 415.5 kilojoules. You don't need to put per mole because in your statement you have already put 1 mole. So that caters for that one. The mean, the average bond contained, the average bond energy, or the average bond energy, the average bond energy contained between chlorine, carbon and hydrogen bond in 1 mole of methane sample is, or if you want, you don't put sample, you just say contained in 1 mole of methane is 415.5 kilojoules. You have explained. How is it different from the bromine in case A? How it is different is that bond dissociation energy is the energy required to break the bond. Bond enthalpy, and in again, this is not an average. Here, for starters, this is an average, meaning if you look at a methane molecule has 4 CH bonds. So all 4 of those have an average of this. But here, it's not an average. And again, this is the bond, the energy that is contained in this bond here. Here, this is the energy needed to break that bond, irrespective of this energy also being the bond energy of this particular element, but this time it is being used